Okay, so now we're going to do an example of a single sample t-test from Chapter 9. So our prompt says, to evaluate the effect of a treatment, a sample of 9 people is obtained from a population with a population mean of 40. And after treatment, that sample has a mean of 33, and we have a standard deviation, sample standard deviation of 9. So the question is there a significant difference between our population and our sample? So a couple things to note here. We don't have a population standard deviation, and the reason that we don't have a population standard deviation is because that's the whole point. For single sample t-test, we don't have population standard deviation data. We only have population mean. So in order to do this, in order to find out if there's a significant difference between sample and population, we have to do a single sample t-test. If we were to have our population standard deviation and our population mean, we would run a z-test like we did in Chapter 8. However, we don't have that data. That data is not given to us. So we do a single sample t-test. So this is how we're going to set this up. The first thing that we're going to do is we're going to talk about our null and our alternative hypotheses. That's the first thing that we're going to do. So null, as you remember, is denoted HO. And that's going to say that there is no significant difference between our population and our sample. So no significant difference between population and sample. Alternative hypothesis, remember, can be written a few different ways. Let me go ahead and add a little bit more before we move forward to our prompt. So we're going to be working with an alpha level of 0.05. We talked about that in the lecture. Our alpha level is going to be 0.05. Most of the time, that's what our alpha level is going to be set to. And that's kind of the standard. Sometimes you'll see some deviation from this, but not too much. We're going to be doing a two-tailed test. What that means is that we are looking for extremes on either side of the distribution, not positive or negative. We're looking for both. So we're running a two-tailed test. We're looking for extremes on both sides of the distribution, both sides of the distribution. So because we are doing a two-tailed test, this is what my alternative hypothesis is going to look like. We're going to write it like this. Our population and our sample are not equal. Significant difference. So that's how you would do your null and your alternative hypotheses. Next, we're going to go ahead and set up our T equation. So if you remember from our slides, this is the formula for T. For our t-test, we've got our sample mean. It's very similar to our Z formula that we talked about in Chapter 8. However, we've got sample standard error at the bottom instead of population standard error, where our sample standard error is sample standard deviation over the square root of n. So these are the formulas that we're working with. We have all of our pieces here to work this out. So let me get a different color. T. Does that show up? No, that's not very good. I'll just keep it, I guess. So T is our sample mean, which we were told was 33 in the problem, minus population mean, which we were also given, 40, over our sample standard error, which we can combine here. We can put both of these formulas together into one. It's easier usually to do that way so you're not doing several steps. However, you can do it separately like this. You can find one and then find the other. Or you can combine the two if you'd like, whichever is easier for you. So we have our sample standard deviation is 9. We put that over the square root of our n, which is also 9. So that is our t equation. Okay. So 33 minus 40 is going to give us -7 over 9 over 3, -7 over 3 again when we do this division. We divide 7 by 3 and we get 2.33, -2.33. So that is our t value that we get. That's our answer. However, we don't know if this is significant yet. We've got to go to our t table in order to determine that. Just like our z examples, I highly suggest you drawing out the distribution in order to understand what's going on. Before we go to the t table, however, there is one piece of information that we do need. We need our degrees of freedom. And remember that degrees of freedom is just n minus 1. So in this case, that is, where's our n? 9 minus 1. Our degrees of freedom is 8. So that is the last piece of information we need before moving on to the t table to find our critical value. So now we're going to go to the t table to find our critical value to see if our t result exceeds our critical value to see if we have a significant result. Okay, so our t table, that's posted on Moodle. I'm pulling mine up right now. Where is it? Okay, so I've now gotten my t table. I'm going to share my screen. Okay, so a couple notes about reading the t table. So remember that we have to know if we want a two-tailed test or a one-tailed test. And we also need to know our alpha level. This helps us find our critical value. So that's the whole point of coming to the t table, is to find our critical value. So in order to find our critical value, we need to know if we are running a two-tailed test or a one-tailed test, and we need to know what our alpha level is. And if you remember what I said earlier, most of the time that alpha level is going to be 0.05. And the last piece of information that you will need is your degrees of freedom. And we have all three pieces of this information for this problem. So I told you earlier that we are doing a two-tailed test and that our alpha level is 0.05, and we found that our degrees of freedom is 8. So we have all those pieces together. So this will let me annotate here. Okay, so we were doing a two-tailed test, and our alpha level is 0.05. So that means that we want this column here, our 0.05 alpha level. Our degrees of freedom is 8, so we come over here, and we see that our critical value, sorry for my lack of art skills here, but our critical value is 2.306. We know that because we're running a two-tailed test, alpha level 0.05, degrees of freedom 8. So our critical value for this one is 2.306. So let me get up here. value is 2.306. Now we got to see if our critical value allows us to retain or reject the null hypothesis. So like I was saying earlier, it's very helpful to draw this out. Again, mean 0. Our t is 2.33. Our critical value in this case is 2.306 on both sides because we're doing a two-tailed t-test. So anytime we've got a two-tailed t-test happening here, our critical value is on both sides of the distribution here. So we've got a negative 2.306 and a positive 2.306. And now I'm going to shade in my rejection region. So if our data fall in this shaded region, we can reject the null hypothesis. So let's look at our t result that we actually got. We got a negative 2.33. So that's going to fall really close here. However, it does fall in the shaded region. Negative 2.33 falls in that blue space. So that means that we reject the null hypothesis. So I'm running out of keyboard. Reject. We're going to reject the null hypothesis. In other words, there is a significant difference between our population and our sample. We reject the null hypothesis. So that is how you would come to that conclusion there. Okay, now we can take this data here, our results here, and come up with our confidence intervals and our effect size, our measure of effect size, to see what the magnitude of our difference is between our sample and our population. So now let's go ahead and do that step. So now we have determined that there is a significant difference. So now in our next steps, we're going to do our confidence interval to see what interval we expect our data to fall in. And then next, we're going to do our measures of effect size, which tell us how big the difference between our sample and our population is. So I'm going to erase some of this stuff here so that we've got room. I'm going to take away our hypotheses. I'm going to keep our critical value because we'll need that. I'm going to erase this. I'm going to write our t-value that we have from our previous step. We found that our t-value is negative 2.33, so I'll put that up here for reference because we will need that. Okay, so the first thing that we're going to do is find our confidence intervals. If you remember from the lecture, our confidence intervals is the space between which we expect our data to fall. So our formula for confidence intervals is very simple. We have our lower level confidence interval, and we find that by doing our sample mean minus our critical value times our standard error for the sample. So let's go ahead and find our lower limit. It's very simple. So we already have our sample mean is 33. Our critical value we found was 2.306 in our previous step. So 2.306 is our critical value. And we already found our standard error, but I totally erased it. I have it written down here though. Let's see. What was it? It was 3. So our standard error was 3. We found that in our previous step when we were doing our t formula. So our standard error is just the denominator in our t formula. And we found earlier that that was 3. So here is your formula for your lower limit of your confidence interval. So we're going to go 33 minus, and you're going to do 2.306 times 3, and we get 6.92. When you do that subtraction, 33 minus 6.92, we get 26.08 as our lower limit. Now we're going to find our upper limit. So this is the upper part of where we expect our data to fall. And this formula is very similar to the lower limit. It's just sample mean plus critical value times standard error. So same numbers, except instead of subtracting, we're adding. So here we're going to go 33 plus 2.306 times 3, which is our standard error. So we've already done this multiplication here, so 33 plus 6.92. When we do that addition, we get 33 plus 6.92 gives us 39.92. So you write your 99%, or I'm sorry, your 95% confidence interval like this. I'm running out of room. 26.8, 39.92. You'd write it like this. So that's how you would do it if you're writing it in a sentence form. So that is your 95% confidence interval. And the reason that it's 95% confidence interval and not 99% is because we have an alpha level of 0.05. When you have an alpha level of 0.05, we have a 95% confidence interval. If you have an alpha level of 0.01, you have a 99% confidence interval. So that's what's happening there. So this is how you do confidence intervals for a single sample t-test. Now let's go ahead and find our effect size, our Cohen's d. So we don't need this stuff here. So our formula for Cohen's d is sample mean minus population mean over sample standard deviation. So very simple formula there. So we've got all the information that we need already. Our sample mean is 33. Population mean 40. Sample standard deviation was 9. -7 over 9 gives us -0.78. So a couple notes about effect size and Cohen's d. Cohen's d is a measure of effect size that works off of absolute values. So regardless of whether or not you have a negative or positive number, you're still looking at your numbers here. So we have got, if you cover up the negative sign, we've got a Cohen's d value of 0.78. And if you go back to your little guide that I have in your slides on how to interpret Cohen's d, which I can pull up now. Here we go. So if you see here, this is on slide 60 of your chapter 9 slides. We see that a Cohen's d effect of 0.2 is small, medium 0.5, large effect 0.8. However, let me say this. These numbers are kind of flexible. So you can say here that 0.78 is a large effect because it is very close to 8. So I would call this a large effect. So you've got a large effect happening here. So not only do we have a significant difference between our sample and our population, but we have a large difference. And the reason that we know that is because we calculated our Cohen's d, and it told us that we have a large effect happening. So basically that is, from beginning to end, the steps of a single sample t-test. If you have any questions about single sample t-test from chapter 9, of course, shoot me an email and I can answer any questions that you may have.